Hi, today I'm very happy to have with me my former PhD supervisor, my mentor and friend, Stephen Hashmi. And after a short introduction, he's going to talk about gold catalysis for organic synthesis. He has done his PhD with Günther Scheimies in 1991, went on to do a postdoc until 1993 with Barry Trost. Finished his habilitation with Mulzer in Berlin and Frankfurt in 1998. And after several guest stays, he became a substitute prof in 1999 in Marburg and later in Frankfurt, and got his first professorship in 2001 in Stuttgart. He then moved to Heidelberg in 2007, where he went on to bring on amazing chemistry, amazing gold catalysis in general, and where I met him later when I started my PhD with him in 2014. Now on to Stephen. Thanks for being here.
Yeah, Florian, thank you so much for the kind introduction. This is an excellent opportunity in these difficult times to address a wider audience via these electronic methods. I'm not very skilled in this, but I will give my best to actually do this today. So, Gold Catalysis for Organic Synthesis is the title, and you see I'm still located at Heidelberg University in German, Universität Heidelberg, which goes back to 1386, as you see reflected by this medieval old seal, which is like the icon of our university in this case. If you look closely to gold, and here you see a beautiful 1 kilogram gold bar, a nice thing to have, very expensive these days. But, well, if you look at the activities in catalysis research, then you find an important statement that traditionally, due to its apparent inertness, gold has been considered unreactive and thus catalytically dead. And this was still in a summary on the field written by Hubert Schmidbauer, famous inorganic stoichiometric organogold chemist in 1995 in this article. And in the meantime, we have 2020, things have totally changed. Catalysis by gold, both heterogeneous and homogeneous, has become a tremendously active field, really contributing also to the methodology arsenal of organic chemistry, and I will show you some recent aspects and older aspects and fundamentals of this chemistry today. Another point, of course, is the price of gold. The gold bar is like a synonym for highly expensive, high value, and things like this. But if you look in the field of catalysis, there are industrial processes on megaton scale run with platinum complexes and with rhodium complexes, both, especially in the rhodium case, homogeneous catalysts for the hydrophobination, for example, 18 megatons or more every year. And this works on industrial scale. So for gold, technically it should also be no problem, especially as the recycling of gold has been much better developed over the years than these recyclings of these two metals, because gold is in so many things, consumer electronics, gold in medicine, gold in other applications, and the recycling is very well developed already. So if you look at the field as a whole, in 2016, I've summarized this. I have stopped to update this because the trend is very much the same. We had well over 100 groups worldwide working on homogeneous gold catalyzed reactions. It wasn't always this way. If you look here, the time as the horizontal axis and the numbers of publications as the vertical axis, you see most of this is empty. And it was only in 1976, in this little blip, barely visible, when Armin de Meyer worked with strained compounds and found an amazing rearrangement, which he also did with a homogeneous gold catalyst in a publication. So this little one paper. And then it took another 10 years until the team in the group of Professor Ito, whom you see here, together with his nowadays famous students Sawamura and Hayashi, worked on the first catalytic asymmetric aldol reaction with gold catalysts. And in fact, this whole kind of pre-peak, this little flat hill here up to 2000, is a series of about 35 to 40 papers on exactly one reaction. Why didn't the field take off exponentially then? They kind of intrinsically killed it by doing thorough scientific investigations and studying the analogous silver complexes in the same reaction, and they found essentially the same reactivity, the same yields, the same diastereomeric excess and EE values in their catalytic asymmetric aldol reaction. So it was interesting to see that gold can do something, but at the same time, why would you use gold if you can use silver instead? Another milestone was first in 1989, so only 3 years after Ito, and then 9 years later by Henry Teles for gold 1 that Utimoto had gold 3, the hydratation of alkynes, a reaction you know from the basic organic lecture for mercury, but with gold this can be done much more efficient and in a much more environmentally friendly way. And that was in 1998 when Teles reported very good turnover numbers already for this kind of reaction. But still the field didn't take off because people thought, okay, now gold can something which we could also do but with other metals, so there's nothing actually new. And this put my group into a privileged reaction. In these 2 papers from the year 2000, which are highly cited now, we could show that we can form heterocycles and new CC bonds, here also additional CC bonds and phenols in a kind of ene-ine reaction. A furan-ine is an ene-ine, so actually this was the first ene-ine ever used in gold catalysis. And this made people really see, oh, there's huge synthetic potential, and this is why subsequently the field literally exploded. So nowadays in the group, we work on catalyst preparation, methodology development, mechanistic studies, and a little bit in applications in synthesis. We have some few papers on natural product synthesis, very few, but actually at the moment we are working very intensively in the field of synthesis for material science using gold catalysis. So what are the catalysts in the field? Well, gold has 2 oxidation states which are important, gold 3 and gold 1 in homogeneous catalysis. And gold 3 prefers nitrogen, or oxygen, and always has a square planar coordination geometry. Now, if you look at complexes, for example, this NO complex was very nice in the context of mechanistic studies. This NO complex is even nowadays commercially from Aldrich, and you find literally like 100 to 200 publications which have actually used it. Together with JM, we introduced this into the field of catalysis. And here you see an NN ligand. Typically, solubility is very low, so we used long alkyl chains to at least grant some solubility. And all this gold 3 chemistry, which nowadays has a kind of revival, we did as early as 2004, as you see in this key paper from these ligand stabilized gold 3 systems. I want to stress, I mentioned him before, Uchimoto in 1987 was the first one to use gold 3 complexes in homogeneous gold catalysis. Gold 1 is the other very, very important oxidation state, and you see it's softer, it prefers phosphorus or in heterocyclic carbene ligands, and always has a linear coordination geometry, which in inorganic complexes is quite unusual. Typically you have square planar systems or octahedral systems. But from your basic inorganic chemistry lecture, you might remember that some organomercury or mercury complexes in general can have linear coordination geometry. So it's not completely unknown to all of you. Complexes are so easy to make. I can tell you literally my mother can do this, no problem. She's over 90 and she can make this. So all you need is a phosphorus ligand in this case, but you can also have other ligand systems. And this example is representative for any phosphane or phosphide you can buy. Here it's specifically done with Kitphos, where we collaborated with Julian Knight and Simon Doherty from the UK. And it's the tetrahydrothiophene gold 1 chloride. In the old days, you had to make this yourself. Nowadays, you can simply buy this. You mix them without any special precautions. And there you go. Within a few minutes, you have complete ligand exchange. And these complexes often are obtained in quantitative units. Of course, due to the linear coordination, this is coordinatively saturated, and we need to rip off the chloroligand to generate a free coordination site for the substrate, a simple silver salt, and very often we use the NTF2- counteranion, which transfers to these systems. Fabien Gagos from École Polytechnique, nowadays at the University of Ottawa, has introduced this counteranion, very successful, to the field of gold catalysis. And if you look at the solid state structures, you see the nitrogen of the non-coordinating counteranion is actually not non-coordinating in the solid state. There's still an interaction, so gold is happy. You can store these complexes even in the activated form for years in the dark in the fridge. But once you put them into solution and offer an unsaturated substrate, say you have ligand exchange and catalysis quickly starts. And with this specific system, we could, for example, achieve 2000 turnovers, which means you need 0.05 mole% of catalyst to fully convert the substrate. And again, I want to mention people who have worked with gold 1 catalysis before us. And apart from Armin de Meyer, it was Ito, which had probably most of the applications on this in the year 1986. Catalyst development is a very important topic in the group. And we developed a modular template synthesis to quickly access gold NHC complexes. And you see the basic principle here. What you need is the same starting material, commercially available THT, tetrahydrothiophene gold chloride, and isonitrile. You can buy some isonitriles. You can easily make some yourselves. And if you remember your basic organic chemistry lecture, people have told you, these are terrible compounds, they are smelly. But if you look closely, for a good ligand, the group R1 will be large to stabilize the gold complex from, for example, getting reduced and form gold clusters. And with the group R1, the vapor pressure is so low that typically you don't smell anything. So what happens? First, this one does not directly react with the amine. It first reacts with the gold to form the isonitrile complex. Then the isonitrile is activated, and only then the amine can add in, and subsequently you have a negative charge here, which bites into the electrophilic group on the other side. You can have simple alkylation to the saturated gold NHC complexes. You can have, with an ester group, acylation to the very difficult to make carbonyl NHC complexes, very interesting class of compounds. It's probably the most simple access you can think about. And here if you have an acetal and a drop of acid, it's a two-stage process. You can first close to the NHC with an alkoxy group, and then with a drop of acid do the elimination to the aromatic NHC ring here in this. And we have published all of this. We have also commented on ligand synthesis in this field and catalysts. We have a patent on that. We have filed that, as you can see, in 2012 with BASF SB. But we are standing on the shoulders of others, and I want to mention my friend Eki Hahn, who has really majorly contributed to the use of isonitriles in this, and my friends from Bero and Kukushkin from Lisbon and from St. Petersburg. And many others have contributed to this as well. And these are most important ones, maybe the most important ones. But everything goes back to Chugayev, who published a paper more than 105 years ago in the Russian Journal of Russian Chemical Society, which first described a principle of, at that time, not an amine, a hydrazine derivative, to react with the platinum coordinated isonitrile. So everything goes back to famous Chugayev. Yeah. Just quickly a glimpse. You can also do larger NHCs, and you see 6-membered ring example here. This works using the same principles, and this mini table shows you that it's really a modular process, and you can, in a very short time, if you have some building blocks, make all these different combinations, because you bring together 3 different components, the metal complex, the isonitrile, and the amine. And so you can make a big variety in a short time. And importantly, of course, the groups R in the 6-membered ring NHC come closer to the gold center and influence the substrate side more strongly than in the 5-membered ring, for example. And this is to show you the functional group tolerance. Even a free hydroxy group is tolerated and works quite nicely. You can make this, and you see the crystal structure fully confirms the connectivity. And you can do subsequent chemistry, for example, allylation. And now you have an organometallic compound, which potentially, if you have the desire, you can use this as an entry point for olefin metathesis or other things, surface attachment, binuclear organometallic complexes, a lot of things. Not only catalysis can benefit from this methodology. And here you see the crystal structure again confirming the connectivity. So now, after we have some catalysts, the question is, what are classical reactivity patterns in the field? And well, if you look at it, it's very simple. Especially the gold-1 catalysts, but all the gold-3 catalysts with gold ligand systems are considered to be soft. And soft systems like to coordinate carbon-carbon multiple bonds in olefins, alkenes, and alkynes. And then they activate them in a way that the attack of a nucleophile is facilitated. It becomes orders of magnitude faster, and gold is probably the best catalyst among all catalysts known for olefin activation for that nucleophilic attack. So what happens? We have computed that. It's much better, for example, than platinum, which in the periodic table is next to gold and has at least comparable relativistic effects. And gold is much better also than platinum with this respect. And then you see, after the first attack, the nucleophile splits off a proton, and you have an alkyl or vinyl gold intermediate. And what happens next? An electrophile comes along and replaces the gold, which is liberated to enter the next catalytic cycle, and you have a netto addition. In many cases, the electrophile is the proton from here. That's a very simple addition. But, and this has been demonstrated by hundreds of papers, this can be something else: sulfur electrophiles, nitrogen electrophiles, carbon electrophiles, all kinds of electrophiles has been used, halogens, and so on. And so this gives you a very rich chemistry. The reactions can be intra or intermolecular, and you can have these 3 substrates. And by this, you can see how many new methods can be developed basing on this very simple principles. And I want to stress that gold is isohyptic in this case, so we don't change the oxidation state. It's not like palladium catalysis, oxidative addition, reductive elimination. It stays the same. It's gold 1 here, then it will be gold 1 here, and it's gold 1 to leave. There's a very important variation of this principle, which I address a little later. I stay here with the first representative example. I love this example because it's a little bit like gymnastics now to warm up for the more complex reactions. So a simple substrate like this, in the form which you see here, hydroxy groups in the zigzag form of the carbon chain on the same side, has 2 reactive groups, 2 alkynes, and 2 reactive nucleophilic groups in the same molecule. And now you can ask, what is going to happen if I subject this to a gold catalyst? And it shows you get these polyheterocyclic systems, very rigid systems, placing 2 groups R in a known, well-defined distance in space. Can be interesting in material science. And the crystal structure showed us that for one derivative, of course, one is oxygen, the other one is oxygen, and the third one is also oxygen. Where does this one come from? It's water. Typically, gold catalysis is completely tolerant to water. No problem. You don't need to exclude humidity. You don't need to exclude oxygen from air. So no special precautions. People have termed this open flask conditions. Now, knowing this, Here in this specific case, of course, you can exclude water and add other, maybe not so strong nucleophiles. And we have done this for anilines, which are very weak nitrogen nucleophiles. And even then you can tailor-make this NOO heterocycle. So what's the mechanism? Now let's get into this. First, gold, of course, coordinates. The alkynyl groups and the hydroxy groups are homotopic. But once you have coordinated one of them, the hydroxy groups get heterotopic. And the question is which one cyclizes? And there's a very simple rule. Gold follows basic chemical principles. That's very nice. You don't have to learn something new. Markovnikov research selectivity applies here. And this means that if we use this hydroxy group, we're close to a 5-membered ring. This one would lead to a strained 4-membered ring, and this is why this one wins. And we always have an anti-addition, so gold and the incoming nucleophile come from different sides to the newly formed double bond. So at the end, yeah, this one adds in, we have the proton coming back. Protodesauration is the process here. In the 5-exo decyclization, we form the first 5-membered ring with exocyclic double bond. Now you see the second hydroxy group, if we start from this diastereoisomer of the starting material, and the alkyne are on the same side of the newly formed 5-membered ring, which means the second cyclization doesn't depend on a special conformation. This one needs a special conformation much more, and the second cyclization is faster. So we cannot stop here. We quickly do another 5-exo decyclization, and we end up with this situation, a bicyclic system with 2 exocyclic double bonds. And in fact, if you now don't have any nucleophile in here, you can stop here, and we could prove this, the crystal structure of exactly that authentic intermediate of gold catalysis. If we resubject this to the gold catalyst in the presence of a nucleophile, we go all the way to the final product. Now comes something very exciting, which is different from classical organic synthesis. Since gold is very big with a ligand and so on, it sits on the exo phase of the bicycle. Gold, the catalyst, will sit exo. Typical in organic chemistry, the reagent will attack a bicycle of this time from the exo phase of the olefin. Now it sits exo, and this forces the nucleophile, the reagent, due to the anti-addition to the endo phase. So this has to attack endo. And this is why after the first nucleophilic addition, the second one has to close a bicycle and doesn't lead to polymerization. If that would be exo, it cannot reach the other side in an intramolecular manner, and we would have polymers and oligomers. But this way, we get this cyclization efficiently, which leads to this product. And if you draw it in a different way, it's this one. Interestingly, this is the kinetic product. The thermodynamic product is a different one. If we use more forcing conditions to the initial product, we get these oxobicyclic ketones. Crystal structure fully confirms that, and this looks like a substructure of some nature products of the terpene type. So now, if we change this, use this, sorry, an open chain carbene ligand, we can do the first cyclization to the cage. And then all we need, everything stays in the flask, only we rotoweb off the solvent, exchanges by methanol, higher temperature 1 pot, we go to the oxobicyclic ketone. This nicely reveals a difficulty. This way, this is highly efficient. But retrosynthesis, to disconnect this oxobicyclic ketone to this open chain starting material, is very challenging. So it's an interesting tool, but a big challenge for retrosynthetic analysis. Good. Let's get more tightly into this. So here we have a very unusual reaction. We start with a triple bond in the substrate, and in the product at the same carbon atoms, we still have a triple bond. But on the other hand, we have a conversion. So very unusual in gold catalysis. What's going on? Our hypothesis was, well, this oxygen obviously is a nucleophile, and this has been studied. 3,3 sigma tropic rearrangement generates an ester of an alene. And now the gold can keep co-cyclization, and this triple bond of the alene, double bond of the alene, is in nice distance to the nucleophilic carbon of this Michael acceptor. The terminal position is not very nucleophilic, but this one. So activated electrophilic attack here at this still nucleophilic position, closest to this carbocation, and the group R1 typically is an aryl group, so we have a benzylic position which stabilizes the system. The next thing is we have an acyl group migration. There are two possibilities. This oxygen would migrate via a 6-membered ring, but that would be a trans-annihilation to a 5-membered ring, and this one would migrate via a 7-membered ring, which you see here, which is maybe more easy to achieve in a bicyclic system with trans-annihilation to a 5-membered ring. Now we see a red oxygen atom. We introduced that 18 oxygen label, and you clearly see what you would expect in the 7-membered ring intermediate. It should end up at the end as the carbonyl group, which you then can show in mass spectrometry, because the acyl cleavage then will show you this fragment with the oxygen. And it's fully confirmed we go via the 7-membered ring intermediate, not via the 6-membered ring intermediate assumed here. Oh, in fact, it's an 8-membered ring intermediate, I see. Okay. We have tested that also apart from esters for the corresponding carbonates, and it works. You see all these substituents are nicely tolerated, and success is there. Even phosphates, organic phosphates can be generated this way. And again, you see you have a very nice scope and it works nicely. So a gold catalysis, in this case, unusual, not consuming the alkyne. And for the phosphates, we did the calculation because obviously we can have different diester isomers with respect to this stereocenter. Trans is clear, but with respect to this one. And we computed, first of all, the 6-membered ring, and you see that would be a transition state and not an intermediate, and it's very high in energy for both diester isomers, while the 8-membered ring is a true intermediate, local minimum. And you see for the observed diester isomer, we have the lowest barriers overall to get the product, so it's in full accord, and we can say we understand this reaction also with regard to the stereoselectivity. Now let's return to the basic reactivity pattern. This is what I've shown you for this very simple reaction, but in the case of the vinyl gold intermediate, we have a second possibility. The electrophile can attack the olefin at the other end, not ipso to gold, at the other end, and this leads to a situation where we would get sigma to gold bonded carbocations, which you can also, if you have back donation from the gold center from the d orbitals, write as a cabine form. So if you now compute that, of course, both represent mesomeric formulas of the same stuff. It's a cabine, more carbocation character here, more double bond character maybe here. If you compute this, and we have done this in collaboration with Johannes Kästner and Johannes Klein and Gerald Knitzinger, you'll see that between 90 and 96% are on this side, and this contribution is very small, and we have done this by DFT intrinsic bond orbital method, which was developed by these two or these three authors, physicochemists. And the nucleophile can be a simple heterocycle like the furan. I've shown you this on the first slide on our reactions which we developed in the year 2000. It's very nice. You can have a tether which can have 1 or 2 atoms, so you can make 5 or 6-membered ring annihilated phenols of this type. And if you have an alkynyl substituent here, you can even in the same pot close another ring to these benzofurans with additional annihilation. This goes back to the year 2000. If you look at the transformation, it's a true spot-to-spot transformation. So the starting material, which is here, time equals 0, simply disappears and the product signals come up. This is the authentic NMR tube, the same one all the time, and nothing else goes on. You see a little bit of funny stuff appearing here, but these are traces. It's a real clean reaction, very nice. And if you do kinetics and compare different catalysts for this system, at that time we were using simple gold 3 chloride, you need to cool to 10 degrees to be able to nicely resolve the kinetics here. At room temperature, it would go all up like a rocket here, and then here. For the other metal complexes, palladium, iridium, rhodium, ruthenium, platinum, you need to heat to 50 degrees centigrade, and you see it's still much lower. So the rate difference are orders of magnitude, especially if you compare to platinum. Also for all the others, the selectivity is not as pronounced as I've shown you on the picture for the gold catalyst. With regard to the mechanistic picture, it was a lot of work, and I have to stress work, computational studies for platinum by Antonio Echeverrin. And so the outcome overall is you probably use the enine substructure, you form the gold carbene cyclopropyl complex, and such cyclopropyl complexes with furans are known to ring open to these olefins. Now, carbene complexes, for example, of rhodium and carbonyl groups, react to carbonyl ylids, and you can have the same oxygen-carbon bond formation here. But rather than having a 1,3 dipole, you have full conjugation through the tether. So the ylid would just be a strange mesomeric formula of the oxypene. While lens tautomeric equilibrium, so up to here is metal catalysis, now comes a pericyclic reaction to form the arene oxide, which then undergoes general acid catalyzed. So the gold, the metal can serve as an acid, as a Lewis acid, but also normal acid you can add, general acid catalyzed ring opening to form the phenol observed here. And now you will say, oh, this is a totally different reactivity pattern in the first step. No, it's just a combination of the two co-reactivity pattern I've shown you. Nucleophilic attack, Markovnikov-Ricci selectivity automatically leads to this intermediate. And you see now you have the electrophile built in the same molecule doing the attack at the black carbon back here, closing the 3-membered ring, forming the carbene species here, and the calculations of Antonio Echeverrin suggest rather than using 2 steps from the 2 mechanistic pictures I've shown you, it's 1 transition state only leading directly to this intermediate. Well, in fact, we could observe the arene oxides and trap them. We could also observe derivatives obtained by hydrolysis of the carbenes, even with the cis configuration. And so the mechanism also in part has been proven experimentally. It's very nice to see that you can make all these systems by using this methodology. A lot of heterocycles become accessible. And the important point is the position of the hydroxy group of the phenol. Classical annihilation would use a phenol, a starting material, and then you generate an electrophilic carbon here, which has 2 possibilities, RT to the hydroxy group or para attack. And if para is not blocked, para wins, and you always easily access these systems, but by classical organic synthesis, you don't access these. By our phenol synthesis, using furans, we have very nice new route to these systems, with the hydroxy group in periposition to the annihilated ring. Then we have looked much wider. What is possible if you use other heteroarenes? And you can make all these systems. I'm not going to detail this, but this shows you that the basic principle can be extended from the furan ring to totally different systems, and again open very fast, synthetic, very fast routes to such extended pi systems. Is it only 5- and 6-membered rings, which classically in organic synthesis close very nicely? My former student Daniel Flesterer, he looked at this using these allenes, the amine and aniline, a weak nucleophile as the nucleophile with a gold catalyst, and he could make 7-membered rings by this methodology. Very nice synthetic scope. You see all these examples, fluoro groups in there, CF3, acceptors, donors, all tolerated. And it works nicely. And here the 7-membered ring is confirmed by X-ray structure analysis of the product. Not only 7-membered heterocycles can close, 7-membered carbocycles. Here in this example, you see an exocyclic double bond, and gold catalysis, for example, doesn't cause an isomerization to the higher substituted endocyclic double bond, like often observed in palladium catalyzed methods for some couplings or something like this. And you see, even thiophene can be used. The sulfur atom of thiophene does not poison the catalyst in these methods. And finally, Daniel wanted to do a synthesis with as many transition metal catalyzed steps involved as possible. So you can clearly see it's a Suzuki coupling here to make the biaryl axis, a simple functional group modification to install the alkyne, the gold catalysis, like before, closes the 7-membered ring. But in these cases, if you want to, you can direct the isomerization to the internal double bond. An allylic oxidation at the methyl group to the allylic alcohol, and then the iridium crab-T type system to achieve the tri-substituted olefin hydrogenation to get, and here you still have adjustment of the biaryl axis, so it's the axis of chirality, a center of chirality, we get one, of course, a racemic isomer of dihydroisosupermol and nature product. So now if you look at the carbene chemistry a little closer, we have observed alkenyl shifts to a carbene center. Here this simple substrate, easily accessible by adding 2 equivalents of alkenyl lithium or Grignard compounds to formic acid esters under the conditions of gold catalysis using a pyridine oxide. And these are conditions which go back to my good friend Li-Ming Zheng in California. He has used them a lot and introduced this methodology as a very efficient synthetic method to the field. And we utilize it here to make these. And what's the outcome? The outcome is a formal group in 3 position of a furan ring. Now, 3 formal furans are very difficult to make because most electrophilic or nucleophilic or methylation methods at the furan ring go to the 2 position and never to the 3 position, only if both 2 positions are blocked. We did some mechanistic investigation, 18 oxygen label in the starting material ends up in the formal group. Carbon 13 in the neighboring one also ends up in the formal group, so these 2 stay together, which indicates there must be an alkenyl shift. After an alkenyl shift, we would have something like this intermediate. So we made it by classical organic synthesis methods, subjected it to the catalyst, and indeed we see the same product. A good indicator that it might be an alkenyl shift. So we looked at the whole situation. The pyridine oxide transfers to the substrate to one of the triple bonds which is coordinated to the gold catalyst, the oxygen atom, to get to carbonyl carbene intermediates. Now remember, there's not really a double bond. I draw it like this because this is how people recognize carbenes very nicely. There's a C plus here dominating, and we can have a 1-2 shift of the alkenyl group. We computed this barrier, Max Hansmann did this. Or we can have a 1-2 shift of the hydrogen atom, which has a higher barrier. So alkenyl shift wins. And this now closes via the more nucleophilic carbonyl oxygen atom. This is a tautomer of an aldehyde, which is less nucleophilic. This is why we have the formal group in the side chain, which is completely confirmed by the computational study. Now, Tao Wang, who actually did this, wanted even more, another oxidant, N-halogen succinimide. And you see, now we do the oxidation, and at the same time, now we get tetra-substitute furans because we also introduce a halogen. And that works nicely for iodination, very efficient halogen plus transfer reagents. And we get all these substrates, so it's fascinating what degree of functionality you can achieve. For example, here 2 tyrifenes, furan ring in the center, iodo and formyl. If you go to bromination, we already have competing protodesirylation. So the Rhone plus transfers not as efficient. If you go to chlorination, it doesn't work anymore. And what about unsymmetrical substrates, which you can also easily prepare? If you have quite similar, electronically similar substituents, here phenyl competing with methoxyphenyl, you have good selectivity, but still the other isomer is also occurring. Typically, the more electron-rich triple bond gets oxidized preferentially. If you have an acceptor and a donor competing, only the one next to the donor gets oxidized, the formal group over here. Steric bulk also works. Mesotyl, TIPS, or terbutyl, only one isomer. You don't need 2 aryls. Alkyl works. Even propygylic ethers works. But if you have a terminal alkyne, the yields really drop. Next step was Hongming. Hongming said, oh, let's lose anthraneals. Very nice nitrogen nucleophiles they add in. They lead to this intermediate at the vinyl gold, to this species at the vinyl gold intermediate. And now, as so often in chemistry, the NO bond fragments, these little arrows indicate that. And we get, instead of an oxygen substituted, a very interesting nitrogen, so imino substituted gold carbene intermediate, with the formal group intrinsically coming from the anthranyl in ortho position. This blocks one ortho position. The other one is still accessible for electrophilic attack of an intermediate. elimination of gold by protodecoration, then finally forms these indoors. And now the formyl group, not like in electrophilic aromatic substitution, where it would be selectively maybe at this position, but some of the other isomers around, it's specifically, only is this isomer specific by the mechanism. And we tested that and it works beautifully. And what you immediately see, gold catalysis also tolerates aryl halides like this aryl bromide here with an acceptor on the aryl ring, or aryl bromide here. So synthetically, unlike palladium, we have synthetic orthogonality to palladium catalysis. Here, we cannot touch, at least with these catalysts, the aryl halide, and subsequent palladium catalyzed reactions then allow us to quickly further modify molecules like this. Now, Hongming once had learned the German word Umpolung, change or reversal of polarity. So he wanted to do one. And the secret was very easy. Instead of an alkyne, he used a propylylic ether. You get to the same intermediate, and it's in the aminocarbene again, like here, but there's a huge difference. Here, due to the lone pairs at oxygen, the hydrogen can undergo a 1,2 hydride shift, and so you get to an enol ether. So instead of the carbene species in the reaction I have shown you before, leading to the 5-membered ring indole ring system, we now have this blue, the same carbon is blue, it's nucleophilic, it reacts with the carbonyl group and forms here the 6-membered ring quinoline system, again with the formyl group in a specific position. And actually this works. You tried these and you see all these substrates. I'm not going to detail them, but you see again, halides are tolerated here and here, and a lot of other groups. It works very nicely. And he has done this with even more substituted groups up to trifluorophenols can still be achieved in a good yield. And from here, then a new student, Songji, he decided to use biaryls. And the idea was very, very good. The same antranyl system, you would get the same initial activation, the same imino gold carbene, but now you have a selectivity choice. This electrophilic carbon can either react in the biaryl system here with the other phenyl group on the left, or with the one coming from the reagent. So if you block this one, we should selectively undergo electrophilic attack, elimination again, and we would form an enamine. The enamine now would attack the formyl group on the other side, and this way we should get a classical kind of nucleophilic addition, elimination sequence, forming big pi systems with nitrogen in there. And this is a topic of a collaborative research center of the German Research Council currently at Heidelberg University. So we were very interested in such motifs and delighted to see that that works. And it works nicely. Again, I'm not going to read all these substrates, but imagine that by classical organic synthesis, you would have to make a donor thiophene acceptor pyridine type extended pi system. That would be a long route. Here we can access this in a very short synthetic route, and the crystal structure fully confirms the connectivity. We have looked at absorption and fluorescence spectra of compounds like that, and started to look at material science with these systems. These are more examples of this type, just to show you what is possible. Again, aryl halide among them. The next one is an intermolecular reaction, again of the antranyl. So here we have an enamide. This should be PG, protecting group, sometimes reverse, sorry for that. And you see same attack. Then we have the aminocarbene intermediate. We have a position here and a position here. If we block this one, otherwise we get to this intermediate. If we block this one, we can selectively attack this aryl group and then get to this intermediate. And now we have a ring system, heterocyclic ring system with 2 nitrogens. And in the meantime, we could also achieve that we install another double bond here. So very interesting in the context of current research focus at Heidelberg again. And these are the examples of the molecules. And amazingly, an internal alkyne even survives here as well. So one of the few examples, as I stressed before. So before, I should go back quickly. You see, we have the antranil, and the antranil also always brings along not only the aminocarbene intermediate, but the whole phenyl group and the formyl group here. That's nice in the methods I've shown you here, but sometimes you don't want that. You only want to transfer the nitrogen without any additional stuff on it. And we figured out that works very nice with sulfilamines as nitrine transfer reagents. And there are many ways to make them. I'm not going to discuss them. I simply list them here and on the next slide here. And in fact, I have to tell you, probably you feel the same way. Sulfilamines, I didn't know how the structure exactly looked like. So my student came to me and said, oh, I want to try these. And I had to look it up. So it's really like a sulfoxide, but nitrogen instead of the oxygen. What happens? Well, very nicely to see with this activated alkyne, so the sulfinamine and the pi activated alkyne. And due to the donor here, gold always goes for the red carbon, transfers the nitrogen to this carbon, the blue carbon. And then we have an inbuilt nucleophile, if you have a phenyl group, in the same molecule, which is attacked by the carbonyl group, annihilation also leading to indoles in this specific case. But it's not the simple indole system. Now we have a protected amino indole system. Works nicely. I'm not going to discuss the details, but again, you see amazing functional group tolerance. For example, the alkynyl bromide can be used and can further be modified. So it's ideally set up for lead structure finding, for example, in pharmaceutical or medicinal chemistry. Here you see more examples of this type. So Xianhai, who worked on this, has produced a whole series of papers. And you see even a bidirectional synthesis still gives a reasonable yield of this substrate. I should mention most sulfilamines are crystalline compounds which you can store for a long time. So especially in the explorative lead finding phase of pharmaceuticals, this is of interest because it's an easy to handle reagent which works really nicely. And of course, the production then can be done in a totally different way. Here you see another system where you have an additional aryl group on nitrogen. Now the carbene intermediate can cyclopropionate the aryl group and leading to these three-membered ring systems. And again, this works nicely. You see all these examples in excellent yields could be prepared very easy in an intramolecular reaction. And Xianhai extended these systems. You see here sulfilamine based on or carrying an additional imine. Same principle. Blue nitrogen goes to the blue carbon of the activated system, they go to the red carbon, we get the aminocarbene intermediate. Now our inbuilt nucleophile is not an aryl group, it's the lone pair at this nitrogen. Nucleophilic attack, elimination, at the end leads again to these systems, and now we have 3 nitrogen atoms in it. The scope is nice, and you can, I think, guess if you're a pharmaceutical chemist that big variation and a high functional group tolerance to these systems, again, may be useful for quick further modification by palladium or other coupling methods is a very nice thing. And here you see more examples of this type. So Xianhai has worked very hard together with Lina Song, who was also involved in this, to make all these systems. And finally, they took these sulfilamines based on carboxylic acid amides. Same principle, activation, blue to blue, red to red. We get the aminocarbene intermediate. Our nucleophile now is the oxygen atom. Attack, elimination, and we get these 5-membered rings, NO oxazoles, and it's an amino oxazole in this case. And again, the protecting group from the starting material carries through to be a protecting group and a product, of course. And here you see some examples just to have you inspired about the possibilities. So, for example, we can have a Thiophene ring again, it works. So we have sulfur, oxygen, nitrogen, nitrogen on our heterocycles, or here bidirectional synthesis. Yield goes down a little bit, but again, it's the fastness of the synthetic excess, it's the shortness of the route, which is the synthetically attractive thing in these cases. And there are more examples, so they have used IQ substrates and similar things, and have also conducted the synthesis in very little more than 1 gram scale of product, 85% isolated yield of that. Let me address the synthesis of azolines to get into material science a little bit. If you have two, you see it's the same molecule just turned around, two alkynes in an intramolecular reaction with a gold catalyst, it will pi coordinate, gold preferentially coordinating to the position which is activated by the donor. So the more nucleophilic position, gold will go there. This will be electrophilic. It will bite into the next alkyne in the same way, generating this intermediate. And now you see this vinyl cation can attack the neighboring aryl substituent, then cleave off a proton, do the protodeceleration here, and this way we get naphthalines with 3 aryl groups here. Now you will say, okay, if you do a Scholl reaction, you get a nice big conjugated system, but Scholl reactions with 2 donors and an acceptor in the middle don't work very nice. We've tested that, it's a mess. Here's the crystal structure confirming everything. But, and this is now the interesting part, if you have a fluorosubstituent on one of the rings of the phenyl groups on the end, the whole reaction pathway changes. You get directly by an intramolecular reaction of 2 of these an azoline. We have done this. All these azolines can easily be formed. Here's a crystal structure confirming the connectivity again. And this is just a hand-waving mechanistic explanation. Coordination in the way before, gold goes to the more nucleophilic carbon atom, the electrophilic one attacks the other one. In the same way, carbocation or vinyl cation here, and now attacking the ipso position, leading to the spiral intermediate. And the ring, the 1-2 shift, Wagner-Meerwein shift, now leads to the ring expansion. We must have the 5-membered ring. Ring expansion generates this 7-membered ring after ring opening, cycloopenation ring opening. And at the end, this leads to the finally observed azoline system with its nice color. And the fluorosubstituent, which we need to induce that reactivity, this to direct everything to this pathway, it's not just the stupid fluorosubstituents, because fluorosubstituents on azolines can be exchanged very conveniently by nucleophilic substitution, using N nucleophiles here, here, and here. Also here, using oxygen nucleophiles, sulfur nucleophiles, you see here with a bromo group, and even twofold. So it's not only a directing instrument, which subsequently is just stupidly hanging around, it can be used for further modification of the substrate. This is what I wanted to show you today. My summary, I personally love gold. I hope you like it too now, and the application in organic synthesis. What are the take-home messages? There are a lot of details in this talk. In the last 20 years, we have published so many things. What are the key features? First of all, keep in mind, gold is not too expensive for catalysis. It can even be used in industry if you have a nice process. Activation for nucleophilic attack is the dominating, by far dominating reactivity pattern. We have the highest reactivity among all known catalytic systems for that reactivity mode. Typically, we don't need precautions. Air and water can be tolerated. If you have a long distance proton transfer, sometimes small water clusters can even be very accelerating for, by serving as a proton shuttle. We mostly have no paramagnetic species, so you can in situ monitor your selectivity, your transfer, your kinetics, your mechanisms, if you have transient species, by NMR spectroscopy. Typically with gold 1, we don't have any beta hydride elimination. We have fully computed that, which means double bonds don't move around. Think about palladium catalysis. often the double bond in the product is not in a position where it initially was. It starts to migrate by, for example, hydropalladation, elimination to the other side, and so on. This doesn't happen with gold catalysis. We have typically isohypsic reactions, so no change in oxidation state. We have a very fast protodecoration, and we have summarized these principles in these articles, and also dual gold catalysis. I think this is this one, which is not in this list, is a new feature introduced in 2013. Many people have worked in the group over the years, very successful crystal structures from these three guys, donations of gold from these companies, and some ligands from these two companies. Without the German Research Council and other funding institutions, all of this work wouldn't have been possible. I'm really grateful to all of them, great support. And this is the institute at Heidelberg University, and my group is mostly located on this floor of this new side wing of the building. All of this floor is mine. I also have some labs in other sections. And every day we look out of the windows and we see this inspiring, shiny golden sculpture in the green garden. Thank you so much for your kind attention.
Thanks for this amazing talk, Stephen. I'm sure everybody enjoyed, and we've seen a massive load of substrates today, but in this format you can gladly or happily go back and pause and have a look at how many substrates Stephen has made over the past years. You have mentioned that it's sometimes quite hard to do the retrosynthesis, to actually see where you could use gold for synthetic challenges. Do you think that the recent developments in automatic retrosynthesis will boost like the application of gold for synthetic challenges? Are searching for
I think a computer can much more easily, of course, see these connectivity patterns generated by gold catalyzed reaction, by complex one. By simple ones it's easy, but by complex ones, a computer of course can easily spot that. At the same time, I'm not a gifted retrosynthetic people, but I know such people. It's like an art. Some of them can do it, and it's simply it flies to their mind from somewhere. They immediately see it. For them, it will probably not be a problem if once they have memorized the connectivity connection of the reaction, they can recognize and do the retrosynthesis. I think it's the kind of more not so gifted applicant who will have difficulties. I have no good solution for that. I've thought about this a lot, and currently I'm in deep discussion and recently exchanged emails with my good friend Dirk Trauner, who is very, very skilled in retrosynthetic analysis. And since years we have the idea to write up something, and I think now in these days we are finally going to do this. I've sent him a whole bunch of references, and I think this might happen soon.
Oh yeah, very nice. I'm looking forward to seeing that. Okay. Apart from that, if anybody wants to reach out with their own questions, feel free to do so. His homepage is hashmi.de, and mail address is hashmi@hashmi.de. Mine is moocs.ac, and thanks very much for watching our video.